Might as well get going. Welcome back from the weekend. Hope you guys had a good weekend. I was in Seattle again. At least I did not have to take a red eye back, which was nice. I did get back late last night, so that was okay. But I hope you guys had a good weekend. Today we are talking about more on graphs. So we started graphs on Wednesday. We're going to get more into detail on one particular algorithm that is like really widespread. It's used in many different applications, and it's like one of the big important ones. In fact, if you do end up interviewing for like tech companies, a lot of times this algorithm comes up because they just want to know if you thought about it and if you know about graphs and if you know about this algorithm in particular. So that said, we'll go through it relatively slowly. Because I don't want to kind of leave anybody behind, because it does take a little bit of processing to kind of figure out what's going on. Once you figure it out, you're like, oh, I get it. That's not too bad. But it does take a little bit of time to kind of process it. So be sure to like ask as many questions as you need during the class. Okay, and there's some good online resources for that algorithm in particular as well. All right, today we're going to talk about Unix tip of the day, symbolic links. There was a Piazza post about that. So this big database that we're using, this big song database, I mentioned it in the report for the handout for the assignment, that it's huge. It's like 250 megabytes, and you don't want to necessarily copy it into your home folder. Well, you don't need to. You can do this thing called a symbolic link to actually make it seem like it's in your home folder when really it's sitting on the department's like web space. So we'll talk about that. I will give you more chance to ask about the final assignment. So if you're still either confused about it or want to talk about various like implementation ideas, we can spend some time doing that. I will mention a little bit about kind of thinking about speed versus trade-off in memory. So I've actually written this program over the last like week or so. I've written this program, I think, 4 different ways, right? Each time I've been trying to compensate for either speed or time or whatever else. But the point, and I wrote it in Python and in C++. And so there's a zillion different ways to do the program, as you may have already been like figuring out as you go along. You can use there's lots of different data structures. I am leaving those decisions up to you, but we have to you have to kind of justify why you're using those things. So we'll talk more about that. And then we'll go into graphs. Okay, questions before we get going into the tip of the day? Okay. So here's what I'm talking about when we have a symbolic link. It's actually really straightforward. Sometimes you'll see it called an alias in various places. But what it means is the file that you want to deal with is somewhere else in your file structure, and you want it to appear as though it's in your one particular directory. For instance, your homework 5 folder. Okay, here's the syntax for using it. ln, which says make a link, -s, which says make it a symbolic link, versus what's called a hard link, which is different. And then you type the file name of the full path, the file name that you are trying to link to. That's where it came from. Okay, so in this case, it's comp15 public HTML assignments HW5 lyricsfull / lyricsfull database.db.txt. That's where it is located. If you are in your folder that you want the link to go into, then you just need to type the name. And it can be any other name, by the way. It doesn't have to be the name that you can call it whatever you want, right? But this name is what you will reference in your own folder. Okay? And what it does is it just places the link there, and it makes it look like your file is there. So let me show you. Let's see. Actually, let me copy it. Copy it out here. OK. All right. So if I happen to be in my temp directory, let me make I think it's actually, I think I already have it. Yep. Make dir homework 5a. cd homework 5a. OK. So right now, as you can see, there's nothing in this folder, right? But if I do this symbolic link, and ln-s, the name of where it's coming from, the name in the folder. If I do an ls now, there it is, right? And my computer actually colors it different to say, hey, there's something special about this one. If you do ls-al to give you a better list of it, take a look. It shows you the name of the file, and then it says, hey, where's it pointing to? Like, where's it coming from? Oh, it's coming from this huge, long thing here, right? And if I can treat it just like any other file. If I remove it, it will only remove my little copy. It won't remove the original. It's a good thing. But I can, and I also can't, you guys won't be able to modify this one. If you do want to modify it, you have to actually make a copy. But if you do like less on it, less lyrics full database, well, there's all the songs, right? And it's all in there. OK? ln-s, soft symbolic links. Questions on that? Shouldn't be too many questions on that. OK. All right, back to homework 5. So let me talk a little bit about the speed of this. OK, in this assignment, I don't know if you've ever looked up, I don't know if you've ever wondered, like, how does somebody like Google search so fast? I don't know if they still do, but at one point Google would actually put the amount of time they took searching for your search, and it's normally like 1/10 of a second, or like 100th of a second, or 300ths of a second or something. I mean, they're kind of bragging. They're like, hey, we're like really fast, right? And they search the entire internet through their index of the entire internet to give you those search results. And it's amazing how they do it. They distribute the load of your search across thousands of computers. So you go and you type in like, you know, where is Miley Cyrus this week, right? And then, because you might want to know, right? And then it immediately pops back the answer. And let's try that. I don't even know if I don't know if I dare. What'll happen is like Google will sell my search information to Amazon, and then I'll start getting like Miley Cyrus CD links at Amazon or something. All right, let's see. Where is, how do you spell Miley? M-I-L-E-Y. This, did I do it wrong? Hang on. Well, you know what? Google knows better. There we go. Miley Cyrus news and photos. Yeah, OK. So anyway, now let's see. Did it say? Yeah, it said here we go. This search actually took half a second, right? Wow, that's actually kind of a long time for Google in this case. But look what it did. It printed out the first like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about 10 or 15 different links, right? And it printed all the context, kind of similar to what you guys are going to have to do. It puts links in there. It puts, it has all this other extra context. Well, they do that by when I type the little search in there. Well, first of all, notice you can. This is a new kind of a newer feature, right? So I can avoid her, right? Or whatever. Can you kind of see it? It actually starts doing the search like while I'm still typing, right? Right. So well, this wasn't the best example, but oh look, this one took 1.6 seconds, right? Yeah. Anyway, but the point is that it sends your search actually to like 1,000 different servers. Each one has a particular little part of the index that they are basically keeping in memory on whatever server it goes to. They do their little search, and then all the results are funneled back to the main server that took your search, and then just spits it out to you. So all of the data is actually kept like in memory somewhere, in RAM somewhere, so that they can do this so fast. There are no like disk accesses necessary for Google to do this, right? It's all throughout. It's all on these like pretty fast servers that they have, and they are able to then get your search back really fast. So when you type anything, it goes to like 1,000 different Google searches. Now we have one computer we're dealing with, okay? And it happens to be a very good computer. It's got 128 different processors in it. And this is the homework server. And it's got something like, no, it's got 64 processors? I forget. No, 128, no, 64. And then 128 gigabytes of memory or something like that. Yeah, it's a pretty beefy machine. Let's put it that way. What it means for your search, though, is you're certainly not going to go back to like the disk and like reread in the data from the files, right? I mean, you could, but it's going to be particularly slow. Remember that like analogy I used about going to disk is like going across the country to get a pencil, like having to drive across the country to get a pencil. It like takes that much longer than just grabbing it. So you're probably not going to want to go back to disk. Well, that means that you've got to have the whole database stored in memory somehow, right? Part of the tricky part about this, one of the trickiest parts, I think, about this assignment is that you have to have the context, which shows the actual words in context in the sentence that they're in or the lyric that they're in. And that means you have to keep like all of those. So you're going to use a lot of memory here, right? How are we going to speed this up, though? Right? Well, we can use more memory by having our database be linked to various particular parts of the songs, for instance. Okay, so you first have to keep all the lyrics in memory. Like that's going to be, and remember, this database is 250 megabytes. So there's 250 megabytes right there, unless you have some other clever way of indexing and keeping just like a pointer to the individual words, real words, plus the actual location. You can maybe figure that out. I was thinking about it over the weekend, and it's trickier. You probably could save a little bit of space that way. But either way, you're going to have to keep the database in there, or keep the lyrics in memory. And then you have to keep a structure with all just the alpha-only words, right? Or, I mean, you could keep a structure of all the words, but that's going to be harder to do. For instance, here, this was a question that somebody had on Piazza. The word, if you do a search for W-E-R-E, okay, that's going to have to match lyrics that are W-E-R-E and were apostrophe R-E and were with a comma after it, because when you get a word into your when you get a word out of the database, it may have the little comma in there, and that's what you're going to end up having to report out when you actually print out the context. Okay, so you have to figure out it's a little trickier. You have to just store the alpha only ones and then somehow link them to the actual words themselves. Lots of different ways to do this. Okay, you could have, here's the way I ended up doing it. Okay, I said I have my database, right, and it's got all the songs in it. It's got a song database, and the songs have all the real lyrics, right, and the real lyrics have the commas and have the apostrophes and all that, right? But I also keep in each song a list of the alpha-only words that link to those other words. Well, a list of alpha-only words in each song that says this word's in here in some form or another, whether it's the alpha-only or the actual with the comma. And then when I do the searches, I do have to look through the actual song and pick out the words. So that takes a little bit of time, right? But remember, you only have to return 10 songs worth. So the object is anything that's going to take a long time, only do it for the songs that you need to do it for. Okay, so that's going to speed things up a little bit. Only do it for the songs you need to do it for. That means don't search through all the different songs if don't search through a whole song if that song isn't going to end up in your final search results. I'll let you figure out what that means, but that's the kind of the idea. Okay, questions on this so far? Anybody have, yeah?
How do you know if the song will end in the top 10?
How do you know if the song is going to end in the top 10? You have to figure that out, right? That's a very good question, right? How do you know if the song is going to end up in the top 10? Well, what makes a song go into the top 10? Right? If I search for, right? There's my search, right? How do I know that a song that says, we were at, the whatever, da 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 da, and then somewhere later it says, were you there too? Whatever. Right? Whatever. Those both, how does it make it into the top 10? What did we say? It's the frequency of the words. So maybe just keep account of the frequency of all the words with each song. Right? Keep a copy of the words of the count in each song. So you just need to look at the count. Then when you get the top 10, so you look through and you say, okay, I know where all my words are. I know all the songs that they're in. Keep that in some list or whatever. That could be a linked list or whatever it is, a hash table, whatever. The list of the words, keep a list of the words where they appear, and then just look through all the songs they appear in and pick out the ones with the top 10. Then, if you need to find the words for the top 10, look through the words. That's going to be very fast. Does that make sense? Yeah. So you have to be clever about the type of structure you're going to use to get to the point where you need to look through. You may need to look through all the words. Now, you can do it a different way. The first program I wrote that does this last week, I actually stored a link to everywhere in each song where each word kept, right? It was kept. And that took like 4.5 gigabytes of memory when it was the database was in it was like really fast, right? No doubt it was really fast, but it was almost too fast. Like it didn't really matter that it was that fast, right? If you can slow down some parts of it that only have to look through a certain small number of things. Okay? All right, other question.
When you say searching for where we are, and all this should all match where. So if I search where, would I get results that have all those?
Yes. Right. So, we're not going to take it anymore, right? Whatever, right? So that's also going to match if it's got an apostrophe. So all those words match in that one song, right? So anytime you see the letters like this, and what it means is you have to strip out, you have to figure out that this is just W-E-R-E without the apostrophe. But I've given you a function, alpha only, that will do that for you. One sec. Rose, you had one, and then back to Veronica. This one.
That would match word, even though it's not the same word?
Yes. Because of the way we're doing it, that matches the same. Because here's what you get. Now, this is the reason, right? Because, well, first of all, we're not worrying about punctuation in the search terms, right? We are stripping everything. So if we type in W-E', what we will strip it down to is W-E-R-E. Like that's what the search term will be. Okay, so that means that it should match this and this. And it's a design decision. I mean, the other problem is, so here's a question for you. If you were doing a search on Google, would you want W-E-R-E to also match W-E-R-E, comma? Sure you would, right? So we're really just saying, okay, instead of worrying about whether or not punctuation makes a whole other distinct word, we're just kind of saying, if it's punctuation, ignore it when you're doing the search. But when you print out the context, we want the punctuation. So that's the like tricky twist to it. One sec, Veronica, and then, yeah.
So say I searched for we. Technically, we had we in it because that's technically the meaning of that word.
Yep.
So that's not going to count.
That is not going to count. You're right. So if you search for we, right, that will not pick up this because we are not searching for parts of words. Okay. If I search for R, the letter R, right, it's not going to match this, and it's not going to match it's not going to match these. So only the word itself. And yes, you're right. There are some parts where you'd want to tweak it if you were doing this for real. Okay. Yeah. Good question though. Peter.
Should we be using alpha only or like alpha and num?
The one I have is alpha and num. So alpha only also includes the numbers as well. So use that one. You can see it. You use the one that also includes. When I say alpha only, I mean letters and numbers in this case. Anything that's not a punctuation or a bracket or something like that. Commas. Yeah.
So when you use the alpha function created to do, like you said, to like make it link to the other, the punctuated.
Yep.
Would that just be a separate function that we use then, or a separate structure?
Would it be a separate function? I'm not sure I understand what you mean, but probably. I mean, it probably would be a separate function. In other words, remember the program that gives you the words gives you this. It gives you it with the punctuation, right? So when you get a word from the database, when you get a word from the file, it's a punctuated word. And then you need to take that punctuated word and store it somewhere so you can get it as a lyric, because punctuation, you need punctuation when you output the lyrics. And that's that. So yeah, so this is it's a little tricky, but again, here's my suggestion. Keep your database such that it has a list of all the alphanumeric only words as well as the lyrics. It's going to be a little bigger, but that's the way you're going to be able to go from the alpha only and say, does the song contain this word? Well, yeah, it has W-E'. That means it does have this one in it. So you're going to have to think about that idea. Okay? Yeah, Ren.
Do I need to worry about punctuating the input?
You do not need to worry about punctuation in the input, except that it will be there for you. In other words, you mean when you ask for a word?
Yeah, I want to search for it.
When you search for a word, no, you do not need to worry about you should strip all the punctuation off of it using the alpha only one. So I can type in the word W-E', but it will match this and all the other W-E-Res.
So search for we are.
You can search for we', But what you should do is have that strip out and only search for the alpha only part of it. Make sense? OK, good. What else? Yeah,
I
Eliza.
don't know that much about the alpha and num function, but is it more efficient for when we're taking in the lyrics to find the words that have punctuation in them and then convert those, or to just convert everything?
Is it more efficient to find the words that have punctuation? Well, you need to find the words that have the punctuation to print the context out. OK, so when you print, we're not going to take it, and you search for W-E-R-E, it's got to print the W-E apostrophe R-E with the capital W too, by the way. Right? So, I mean, you've got to have this whole thing in your database, but you've got to be able to find it with this one. What it means is, like when you're looking through each song, for every word in the song, you've got it in this form. First, convert it to this form, check it, and then return this form. Yeah. Other questions? No? OK. Yeah.
Do you have a mini database?
You do have a mini database. It's just Rick Astley songs. It's all of his songs, as far as I know. All right? I'm Rick-rolling you with this assignment, I guess. Yes?
Are you going to make like one that's in between?
Yeah, I guess I probably should make one that's a little bit. It's got more than one author or artist in it. Yeah, yeah. Although that shouldn't be too hard. I mean, that shouldn't make it much of a difference. But yeah, I'll do it.
Just to test between like the amount of space that you're using.
Oh yeah, that's.
30 and then jumping all the way to storing 170,000.
Yeah, 30 to 170,000 is a big jump. You're right. I'll try to figure something out. Maybe I'll make one that's moderately bigger, but don't want to make it too big. But yeah, moderately bigger. Yeah, 1,000 songs or something. Sure, sure. Yeah, good question.
Extracting a big one using head or something.
Say again. Oh, they could extract. Oh, yeah, that's right.
You know how to use head.
Yeah.
There's not 10,000 lines in the file. They make a little one.
That's true. If you type head, right, that will, and then dash 1,000, I believe. Dash n 1,000. There is? Oh. OK. And then we type lyrics full database. That will give us the first 1,000 lines in the database. So you just, if you want the first 1,000 songs, well, each song's got about 20. Yeah. And then pipe it out, right. And then out to lyrics 1000.txt. Now, you'll have to modify it a little bit to make sure it has the break at the end and it fits the thing. But you could figure that out, yeah. That's the easiest way to create your own. Yeah. OK. Good. Other questions? I'll talk a little bit more on Wednesday. Yeah, Nadia?
You suggested that we could use a set to store certain things.
Yes.
But I was just curious, like, for example, if you wanted to store
You can use a set, yeah.
words,
Uh-huh.
words are first a string. We have to like convert, like, because the read lyrics, it's storing like the artist and the title and the lyrics as all strings.
Yes,
So in
they're
order
all
to-
strings, yeah.
To like convert like the string of lyrics into like a set.
Uh-huh.
How could you? I mean, do you have to declare it like a string and a?
Yeah, I thought my set example did that, but let's see if I can do this. Let's say that you had, if you're going to do a set, right? You do number include, something like that, right? And then in your set, when you declare a set, right, you're going to say set and then what type you want. So it's a string. If you're storing strings, it's going to go like this in angle brackets, and then my set or something like that, right? Or song set or something. Song set, right? That will declare a set of strings. Then you can put the strings individually into that set.
Okay, so.
Okay, yeah.
So then, like, if you've gotten like a set of, or if you've gotten lyrics, then you can like take the lyrics, like the string of lyrics, and
You can put the lyrics.
string of sets.
You can say again.
Like if you in the read it as a read
Yeah.
lyrics function,
Yeah.
you're getting, you're like you get basically like a string of lyrics.
You get one lyric and you get the title and the artist.
Okay. So
Each time it goes through.
then you can like take
Yep.
like that string.
Yep.
And make a set.
Yes, and then you could take that and make it into a string set, or you can also put structures in here too. So my struct of some sort, right? And you can do that. It is a little more advanced than some of the stuff we've talked about in class, but if you want to go through how we might do that, I can show you. Yeah. Okay. Good. Other questions? All right. You'll have another chance on Wednesday to ask some more questions, or office hours, etc. Okay? All right. Let's talk about graphs again. So if we go back to graphs, remember, graphs are node-based structures. They have vertices and edges, okay? But they don't have a real structure like a tree. There are no parents and children and that kind of structure. It's a little more like Wild West kind of structure, in the sense of anybody can point to any other node, and it's not or any other vertex via an edge. So there's no defined structure in that sense. So it makes it a little trickier to deal with. But we see these things a lot in computer science and just in general, as far as things being linked together. Computers or road maps, or distances, things, or like I said the other day, telephone call, routing, and all that. Lots of things are modeled with graphs. Okay? One of the most important features of or algorithms that deal with graphs is finding the shortest path from point A to point B, or from vertex 1 to vertex 7. Okay, that's one of the most important ones. Last week we talked about a shortest path finding algorithm for non-weighted paths. Okay, paths that were just, they were all weighted 1 basically. And we saw how we could go through and do that. Today we're going to talk about one where we have weights on them. Okay, and this is actually named for a guy who's one of the most famous computer scientists, right? His name is Dijkstra. What is his first name? Edward? I forget. Edsker, I think it is. Anyway, he's from, I want to say the Netherlands or something. Anyway, he came up with this algorithm in like the 1950s. It was one of the first big graph-solving algorithms, and it is used like so often. Okay, so we really need to understand what it is. But what it does is it finds the shortest path from, say, node V1 to V6, right? And if we look at this, we can pick it out just by kind of looking at it kind of heuristically, right? Let's see, V1, well, 1's probably, this is not a bad idea. 1 to 8, that would be 9. OK, well, what if we went this way? That's 5 this way, and then another 6. So if we go this way, that looks like a pretty good choice. We can't go this way. We could go this way, 2, 12. Oh, that's already more than 6. So you see how we can figure out from vertex 1 to vertex 6, the shortest path by weight has to be is 1 to 4 to 7 to 6. Does that make sense to everybody? Shortest path non-weighted would just be 1 to 4 to 6, because you can get there in 2 jumps. This is not about jumps, it's about the cost, and the cost is represented in the edge cost, or the edge weight. Okay, that's how we're going to do this. Dijkstra figured out, by the way, I really like this. I really like his name because it's got IJK in it, which is kind of cool, by the way. You don't see that very often. 3 consonants, or 3 letters in a row in a name, not often. His algorithm is known as a greedy algorithm. Okay, you will find greedy algorithms, again, all throughout computer science, right? What a greedy algorithm means is it solves a problem by doing what seems best at the time. It's like, I only can see this far. I'm going to go this way, right? Right? I mean, it's kind of analogous to, let's say you're trying to get from somewhere. Let's say you're in the woods and you're trying to get somewhere. Well, you can't see all the way to the other side of the woods. So you don't know right now what the best path to get to the other side of the woods is. But you see, like, there's a path this way that looks like nice, and everybody's gone on it, the path well traveled, right? And then there's this other one that's got like weeds over it. Nobody's been that way in a while. Well, you're going to pick the one that's easiest to go, like you think is the best choice right now. It might be that the other one would end up getting you there faster, but you'll figure that out eventually. Okay, that's what a greedy algorithm does. Greedy algorithms don't always work. Okay, they're not perfect, and there are cases where they always work, such as this algorithm, but they don't always work in general. Here's an example of another example of a greedy algorithm. Okay, if you've ever worked retail, you probably know this problem very, very well. Not particularly hard, right? You count out change. Okay, if you're counting out change, and let's say you're limited to, well, the change that we have, right? In this case, quarters, dimes, nickels. Forget about 50-cent pieces for right now, or dollar coins. By the way, I'm of the opinion we should just get rid of pennies. I don't know if you guys are too. Pennies should go away. Pennies should go away. Dollar bills should probably go away too. Dollar coins are great. But anyway, Chris Gregg's opinion. So if you count out the quarters first, then the dimes, then the nickels, then the pennies, you will end up with the smallest number of coins in the end, right? That's just the way it's going to work. If you did 15 cents change, first there's no quarters, so you count out a dime, and then you grab two nickels and you're done, or sorry, a nickel and you're done, right? And you've got 2 coins and that's it, right? The only other, that greedy algorithm actually works. What if, okay, we weren't to get rid of the penny, we were instead to decide, let's add a 12-cent coin, because that would be a great idea, right? Let's just say you did, right? If you were to add a 12-cent coin, I'll let you decide what to call it. I've called it a 12 pence. Call it a 12er, a dozer, or something, I don't know. But if you added a 12-cent coin and tried to do a greedy algorithm to get your change, it wouldn't always work for the fewest number of coins, right? Let's take an example. 15 cents change, 1 12 piece, and then you can't do any dimes or nickels because you'd be over the 15 cents, so you go straight to pennies. You end up with 4 coins when you still could have done it with a dime and a nickel. Okay, so the greedy algorithm in this case doesn't work. So when you're building algorithms or when you're looking at algorithms, sometimes you might try a greedy algorithm and it won't always work for examples like this. Okay, questions on that? Greedy means do it in a fashion that you think is best at the time. In this case, it would not be best. I mean, at the time, it seems you're going down and doing it, but it's not the best idea to pick the 12 cent. Okay? All right, so that's the idea of a greedy algorithm. Dijkstra's algorithm is greedy, and it happens to work, so that's a good thing. Here's what it is. Okay, it says, first you pick some start node. This is the idea. Same with last week. You're picking a start node, and you're trying to get from that start node to find the shortest path to all the other nodes. That's the idea. Okay, in this case, we're going to pick V1 as our start node for this one. Here's what it does. It says, I'm going to select the vertex which has the smallest distance among all the ones that I haven't designated as being finished yet. Like they aren't what we call known yet. Okay, they're still considered unknown, and I'll get into what that means in a second. This is kind of a review from last week as well, but in this case, if we don't know that we've already dealt with them, we have to go ahead and choose from that list. Okay, so if we start here, okay, we only have 2 that we can choose from that are, well, that's not true. If we start here, we first look at this one. This one's going to have a length, if we start at V1, it's going to have a distance of 0 to itself. Okay? Before we do anything else, even though you've got all these paths in here, we're going to build a table that says all the other paths are infinity. Like we literally put some sort of designation that says they are as big as they get because we don't know what they are yet. So you're trying to figure out what they are. Okay? At each stage, okay, the algorithm decides whether it's a good idea or not to use a particular weight based on whether it's known yet or whether it's lower than the other distance. We're going to get to an example here. Here's our little table. Okay, it's kind of similar to the table we had before. Here's what our table tells us. It's going to tell us the vertex that we're in the table. So this is how it's laid out. It says whether or not it's known yet, true or false. It says the distance to that vertex from the one that we're starting from. Okay? And this column is going to be like what we think is best so far. From what we know, what the distance is so far that's best. And then this is going to be the previous one, because somehow we're going to need to, we might need to know what the path is at the end, right? Like you can say, oh, it's the shortest path is 12 from 1 to 5. Then you go, well, OK, get me there. Right? Well, you have to know how to get there. So we need to keep something in here that says, how do we get there? That's going to be the other part of the table. OK? That makes sense so far. And here, we're going to start with this table from V1 and try to find the shortest distance to everybody else. Okay, questions so far? Let me ponder that for a sec, because it's a... All right, we get it? That's how the table is going to go. So let's start out. So we know that the distance to vertex 1 is 0. We haven't said that it's known yet, because we haven't dealt with it yet. We haven't actually processed that node yet. Okay, but now we're going to process it. So we're going to process node 1. Okay, and we're going to say, OK, and blue means that it's known. Sorry, you can't. It's tough to read the color up here. But blue means it's known. That does have a true under there, a T under there. OK, we look at vertex 1, and we say, which ones does it point to? Well, it points to 2 and 4. So we can update 2 and 4, because we know that if we're at 0, Going to 2 from 0 is going to take 2 cost, right? A cost of 2. So we can update vertex 2 to be a cost of 2, or a distance of 2. Okay? 4 is the same way. It's just going to be a distance of 1. Everybody else still infinity, because we haven't done those yet. We've done vertex 1, it's 0. We're now doing 2 and 4, and we've updated those. And by the way, we said what the previous one. It says, hey, vertex 2 and 4, so far the shortest path is from vertex 1. From vertex 1, path of 2, distance of 2, from vertex 1, distance of 1 for V4 and V2. Questions on that so far? Anybody have anything like that makes sense? OK, this is how the algorithm is working. What's the next one we're going to look at? Vertex 4. It's going to be vertex 4 because of the unknowns, which are 2, 3, 4, 5, 6, 7. Even though we know where our temporary is, we haven't processed it yet, so it's not known yet. Of those, the shortest one is going to be 4, so we have to deal with that one next. If there's ties, you get to choose. Right? Ties, you get to choose. But if there's a shortest one of the ones we haven't looked at yet, pick that one. So we have to go to 4. All right? So we go to 4. And we say, mark it as complete, because we now know that's where the next shortest is going to be. So we take 4, we mark it as known. Whoops, I forgot to do the color now. Well, that's probably better for seeing it. Marked as known. Okay? And it has edges that point to 3, 5, 6, and 7. So we get to check all those. We haven't actually seen any of those yet, so they're going to go from infinity to whatever the total distance is from 4 to that node, those nodes. So 4, it's already 1. So to get to 5, it's going to be a total of 3. 3. And the previous node is vertex 4, or previous vertex is vertex 4. Okay? Same thing for 6. In this case, it takes 1 and 8, so that's 9 to go to 6. So we make 6. The last one comes from is 4. Now, we already saw that that's not going to be the final answer. Right? Well, the algorithm will take care of it. Okay? All right. Now we're done with, we've updated everybody, and nobody's infinity anymore. That's nice. Right? But we've updated everybody, and now we select of the unknown ones, 2, 3, 5, 6, and 7. We have to pick the next one, the next smallest one. Let's see. 2 has 2, 3, 3, 9, and 5. So we're going to have to pick vertex 2 next. Okay, so we go to vertex 2, and we do the same exact thing, and we set it to known.
But aren't we at vertex 4?
It doesn't matter. It doesn't matter where you are at the point. You look through the table, and you say, OK, we're done with 4. In our table, what's the next one of the ones we haven't dealt with yet? What's the minimum one? So you're not going to go this way, or you're not going to go to any of these ones, because it happens to be this one is the next one in our table that is not known yet and has the smallest distance so far. That's how the algorithm works. Okay? So yeah, you're not following it like you would a tree. Completely different idea. You don't have to follow it. That's why part of the reason we have the tables like this, and we have those adjacency lists. In other words, each for vertex 4, you've got you say, hey, who am I pointing to? I'm pointing to 7, 6, 3, and 5, and that's in a list. That's how we're keeping the list. It's not parent to child relationship. Good question. Okay? All right, so we picked 2. All right. So we look at 2 now, and we say, all right, 2 points to 5, and it points to 4. Vertex 5 and points to vertex 4. OK, so let's see. For vertex 5, let's look at that one first. Let's see. It would take a total of 2 plus 10, 12 to get here. Well, it's already only 3, so we don't need to update it to 12. That would not be a good choice, because it would be too far. You can know that it's already 3. You don't change it because it's less than, it's already less than the one that the setting that it's at, the distance that it's at. So you don't bother setting that. Same thing with 4. 4 is already a distance of 1. If you went from 1 to 2 to 4, it would be 5 total. You don't change it. So we actually didn't change any of the numbers over here, nor did we change where they're, like nobody gets to say my previous one was 2. Like just not, it's not going to happen. Okay? But 2 is now known. And now we've got our list of unknowns still. 3, 5, 6, and 7. What's the smallest? 3 and 5. Okay, so we can pick. In this case, we'll pick 3. Doesn't matter. You can choose each one. I would just choose the one you get to first when you're looking through this list. Okay. All right. So we picked 3. 3 points to 1 and 6. All right, so 1's not going to change. Of course it's not, right? So even though you could get there by going, let's see, 3 was 3 right now. So it's going to be 3, 7 to get here. You're not going to update 1 with 7. Why would you? It's going to be less. It's going to be more than 0. So of course you're not going to do that. Okay? But you are, and your same thing. Are you going to look at 6? 6 would be, let's see, 1. So 3 plus 5 is 8, and right now it was 9. So we're actually going to make it 8 now. We're going to change this one. We're going to say now it's coming from vertex 3. That's its previous now. We've updated it. So far, so good? Okay, I'm purposely going kind of slow through this so you can see the algorithm in action. Okay, then we're going to do 5. 5 is same thing. We mark it. It as known. It only points to 7, and 7 is already a distance of 3, so you don't need to. 7 is already a distance of 5. You do not need to update it because it would be, let's see, 3 plus 6, 9. So it's not going to change. Good? All right. And let's say the only ones left are 6 and 7. We have to pick 7 because it's got the smallest distance. We pick 7. 7 only points to 6. But guess what? We actually now know that 6 was a distance of 8. 7 starts out at a distance of 5, and then we only need to add 1 more to get to 6. So yeah, we are going to update 6. So 6 is now going to get updated, and it's going to just be 6, and it kind of walked its way down to the actual correct answer. Okay? And then finally you deal with 6. 6 actually doesn't actually point to anybody, so we don't need to update anybody. But we're done. Everybody's now known. These are the distances from 1 to those vertexes, and this tells you what the previous one was. Okay? How do I find out the actual? How would I find out the actual path I need to get to, say, vertex 6? Yeah.
Wouldn't you just go to vertex 6 and then follow all the previouses back?
Yeah, you'd follow all the previous's back, right? So you'd go to 6 and you'd say, OK, the previous is 7. That means I go here. Well, what's 7's previous? 7's previous is 4, so that's here. 4's previous is 1, so that's here. What kind of algorithm are we? Or what kind of algorithm? Yeah, that's what I mean. What kind of algorithm is it? It's going to be recursive, right? Because you're going to just go to the previous. You're going to go to the previous one and check its previous until you don't have any more previouses, which means you are back at node that you started at. Okay, it's very simple recursive function here, like super duper simple. Okay. I put a lot of this code, a whole graph and vertex code on the website. So if you want to go look at it, I've tried to comment it a little better than I have in the past. So it's commented relatively well. What it does is it shows you, it will print out. In fact, I'll show it to you. It will, let's see if I can figure out where it is. Yeah, this is an example of what it is. Let's see there. OK, so font's not so big, but notice how when you run it, right? Let's see, which one am I running it on? Yeah, the regular old Dijkstra one. It tells you where it starts, and it does the known. It does the vertex, says known, says the distance, and says the previous node. And then it just, as it goes through, it does this step by step by step and prints out the results as it goes through. And then at the end, it will actually print out the shortest paths as well. So in our case, we wanted to go from 1 to 6. Well, we had to go, and this is for that one I put up on the board. We went 1 to 4 to 7 to 6. Okay? And by the way, the recursive algorithm, it's one of those recursive algorithms that prints out at the end, right? It prints out at the end so that it can do the first one first, right? So it says you're going 1, 2, 4, 2, 7, 2, 6. Okay? It's one of those recursive algorithms. Okay? Questions on that so far? No? OK. Dijkstra's algorithm, I can guarantee you there will be a question about it on the final. I can guarantee you that you will see this in other classes that you take. Okay? If you take algorithms class, you'll hammer this thing for a while, and you'll talk about it. We haven't yet talked about the actual running time yet. Okay? Turns out that it depends how we actually manipulate the vertices. Like, depending on how we do the manipulations, of the, like how we go and check for vertices to see if they're in the list that we want to check next, determines the actual runtime for this. Okay? So let's take a look. We could look at, when we want to, and this is kind of what we probably did in our head when we went through this, right? You could say, OK, look through all the vertices that we have. And if it's not known yet, that would be like, you look at each one, right? And then if it's not known, you can skip it. So we look at this one, then this one, then this one, right? Well, what it means is you have to look through everybody for every loop through the time here, every loop through this algorithm, right? That's not particularly efficient. Okay? It's not efficient in the sense that you have to look for every vertex, you have to look through all the other vertexes, right? Not so great. It's actually on the order of the number of vertices squared. Okay? That's the running time. When Dijkstra first came up with this algorithm, this is the one he published, right? A number of vertices squared algorithm. Now keep in mind this was like the 50s, right? So give him a break if you didn't find the other one, right? Like a better solution. A little bit later, people found other solutions that we're going to talk about. Okay? But that's one way to do it. All right. A better way to do it, okay? Well, by the way, this is my example of tried to make a dense graph. A dense graph would be every vertice points to every other vertice, right? On the order of anyway, right? In other words, all the edges, the number of edges is on the order of v squared. If that's the case, and it's rarely the case that you have graphs like this, right? Rarely the case. But if it is the case, then this algorithm, the way we're doing it, is actually perfectly fine. Because you're going to have to go through all the vertexes anyway. You might as well do it this way. Nothing particularly wrong about that, right? In terms of the number of edges, you're actually linear. And that's the best you're going to do, because you still have to look at all the edges to find the cost between edges, right? And by the way, try to do one of these and get all the edges right. Good luck. Took me a while to write through that little drawing. And the guy next to me on the plane was like, "What are you doing?" No idea. OK, so that's if you are a dense graph, this is actually a perfectly good algorithm way to look through the graphs. However, most of the time it's not. Like most graphs are what we call sparse, which means that they have many fewer edges than they do like vertices squared, right? I mean, like the number of edges are not, there's not an edge for every node to every other node in general. Okay. There's a reason one of the reasons we spent so much time on heaps, because now it comes back to us. Okay, you can actually use a priority queue to figure this out. The whole point of, remember the whole point of this algorithm was to find the node or the vertex with the fewest number, the shortest distance. Like that was the whole point. When you're thinking shortest or greatest or whatever, right, you should automatically start thinking, do I have a structure that gives me biggest or smallest or whatever? Well, it's a heap, right, or a priority queue in this case, OK? So what we can do is instead of looking through this list each time, when you change a distance to a vertex, throw that vertex back into a priority queue, because later we may want to use it, right? And if you get to it later and it's already been marked as known, you can just ignore it, right? So what that does for us is it means that we don't have to go look through. We're gonna automatically in a queue structure look at the first one in is the first one out. We're gonna prioritize them such that the minimum ones end up coming out first, and we will end up saving a lot of time to do that. Okay? We ignore the ones that are already there. I will walk through this slightly faster than the previous one, showing you the priority queue method. Okay? It's the exact same graph as before. Okay? Same sort of situation here. I'm not going to bother with the P column right now to previous one. It's just not necessary, and I want a little more space for the heaps. All right. So you've got a heap here, and sorry, I said queue as if it was first in. This is a priority queue in this case, not an actual queue for this one. OK, so you have your heap, and it starts out with one node in it, or one vertex, which happens to be the one you're starting at. OK, and it has a distance of 0. Okay? You take the min off the heap. Well, the only one on the heap is that one, so it gets taken off. So delete min pulls off vertex 1. Okay? And when you're dealing with 2 and 4, okay, you end up adding them to the heap. Now, because it's a heap, you don't have to worry about whether you take care of 2 or 4, like in what order they're taken care of. They will go onto the heap and then heapify, or when you do the heap insert, they will percolate to the right, they'll bubble up to the right location. Okay? They'll actually bubble up just fine. Okay? So in this case, it ends up with, this is our new heap. 4 with a distance of 1 and 2 with a distance of 2. Good? All right. What do you do now? You delete min again. Delete min gives you 4. Well, you deal with 4. And by the way, it's exactly what we were doing in the previous steps. We just now we're like formalizing it a little bit more. All right, you deal with 4. 4 points to 4 different other vertexes or vertices. So then you add them all to the heap. All right, 2 is in here, and then you put all the others in here, right? And it ends up that the heap ends up looking like this. 2 is on the top. 3 and 5 happen to be the same. Remember we dealt with. We didn't really talk about having the same ones in here. If you want, you can either double up and say there's 2 there, whatever you want as far as your heap goes. In this case, I'm just saying, fine, I'm just going to make them into the same. And it generally works for this. There's a couple tricky parts, but generally works. So anyway, then you've got that, and then you've got 6 and 7 down here. All right, do delete min again. Ta-da, we do delete min. That gives us 2. We deal with 2. Okay? And you have to do 5 and 4. Well, we don't change 4, so actually we don't need to put 4 back in the priority queue. We do change, let's see, we also don't change 5. So in this case, we don't have to don't adjust anybody. Do delete min again. Do delete min again, and you get 3, etc., etc., etc. You see how this is working? Okay. So you get the idea of you're doing this delete min, looking at the minimum one, and you can go through this. I've got all the pieces there to do this. I did not implement the heap for the program online. It's not hard to do. I just haven't gotten there yet. I'll do that and try to post it by the end of today. So you keep going. 5 is going to come off, and then 7 is going to come off, and then 6 is going. Now, by the way, notice something here. 6 is here. We have to put another 6 in there. Because in this case, where was it? It was right here. 6 got changed. This is the one that kept getting changed anyway. 6 got changed. It ends up getting pushed on with its new value there. Okay? In fact, it doesn't really matter that could also change to 8. But it doesn't. The point is that it gets put back on the heap. And now you're going to end up having 2 that might be on the heap at the same time. Okay? And then same thing, you'll end up with a couple there. At the end, you end up with like these 6, but then you deal with it. You grab the 6, which has now got a distance of 6, and you're done. But there's 2 more things on the queue. Well, guess what? Everybody's already known. So when you do delete min, well, you don't need to deal with 6 again because it's already known. So you delete it, and you're done. Okay? We'll go ahead and walk through this, and you'll see that it actually works. Okay? Great. What have we done for the runtime? Well, for each edge now, okay, we have to perform a delete min. Now you'll remember for priority queues, delete min, remember how it works? It takes off the top one, the root, and then takes the last one, puts it at the top, and then bubbles it down appropriately. Right? Well, that's a log n behavior. Okay, so for each time we have to do delete min, it's log based on the number of vertices. So therefore, we've got a total for each edge. We do a total of log of the number of vertices, and therefore our complexity is order number of edges times the log of the number of vertices. Okay, so that's how and that's much better than the vertices squared that we had before. Okay, questions on that one? No? All right. OK, so that's Dijkstra's algorithm in a nutshell. Okay, that's kind of the baseline shortest path searching algorithm. In general, this is the best one you can do. You can use slightly different types of heaps, which will make this a little bit better in terms of complexity. But really, this is about as good as you're going to get. There are other kind of shortest path algorithms that are, again, slightly better, especially given your cases. But this is the big one. This is the one that everybody needs to know. Okay? All right. What if, now I mentioned this on Wednesday, if you have negative costs, you run into some problems. You definitely run into some problems using the Dijkstra algorithm straight away. Okay, let's take a look at this one right here. I have changed some of the edges directions simply so that we didn't have to get any cycles, so negative cost cycles, because negative cost cycles makes it even a little bit trickier. It's not the end of the world, but negative cost cycles makes it even trickier. That means that you could keep going around and around and making the node go lower and lower and lower, right? The cost go lower and lower. In this case, you can't do that. But let's take a look. So in this case, if we want to go from back to 6, or let's say to 4, all right, Dijkstra would say, great, we're going to deal with 4 first, we're going to deal with 1 first. Then we would go deal with 7, right? Because it's actually less. Or actually, maybe you deal with 7 first instead of 1 because of the algorithm, right? But the problem becomes you might end up not count. You might end up saying something is complete or no, you wouldn't. Sorry, you wouldn't actually do. You would always start with the first one. So you do this one first and say that it's known, right? And then you would handle these two, and then you would end up doing vertex 4 and say that it was known. Once you say that it's known, remember, you can't go back and change it because you say, oh, it's already known. I'm not going to change it again, right? Because I'm done. But in this case, if we walk all the way around here and we get to 7 and we go, oh, this negative 40 means that we would end up having to change vertex 4. Blah. That's bad news, right? It ends up screwing up our algorithm. Is there an easy solution to this? Any ideas how we might deal with this?
Why is that a problem? Because you said that if it's lower, if the new path is lower than the other one, we can change it in the table.
If the lower, you can change the table, but the problem is you will already have set this one to known. Remember when we start out, what are besides this one, which the one we're going from starts with a distance of 0. All the other ones start with a distance of what? Infinity, right? Okay, so everybody else is now infinity. Okay, we're going to start with the start because it's the only place we know where to start. So we start with this vertex 1, and we say it's going to be known. So vertex 1 is known. And by the way, let's say we could wrap around to here with a negative 40. Well, if we just immediately set vertex 1 to known, then you're done. Because later you can't go back and change the ones that are known already. That's part of the algorithm. You don't go and change anything that's already known. In fact, you don't even need to look at them. Okay? But the point is, but the point is that in this case, you would make that one known, and then you would set 4 to a distance of 1, 2 to a distance of 2, and you end up getting, then you have to go on to 4, and then you deal with 4, and then you set it to known, and then you're done. Because later you can never change it again. Question?
Could you just add 40 to all the edge?
Good question. Yeah, that's actually not a bad idea. Could you just add 40 to all the edge costs, or 41 maybe? So it's at least positive, right? We don't even need to deal with zeros, right? Let's say that this was actually, if we made this one 40, let's say we made this one 1, and this one 43, and this one 42. Just add 41 to them all. Or you could add 40 to them all, right? Yeah, that's a great idea. Does it work? You got right into my next slide. This is actually a naive approach. Not that you are naive, but that's a great. I mean, it's a good approach. It just happens that what actually happens is paths with more edges become more weighty than the ones with fewer edges. Watch. Okay. Now you've got an issue of going from here to here. This is now not just like it's not 12 anymore, right? It's 43 and 51. You've kind of doubled the problem. Like you've gone from it's 40 more here and 40 more here instead of just a total of 40 more, right? So that actually screws up the algorithm as well. You don't end up doing it. In the program code I gave you, you can test this out, and you can see it has one that says, it has a thing that says add a delta, which is exactly what you would do here, right? And it ends up that you still don't say that this path is actually shortest, as it turns out. And think about it. Let's look. From here to here is 42, right? We said that this should have been the smallest path, right? Well, now it's going to be 43 plus 51 plus 47 plus 1. It's not smaller than this one either. So very good idea. In fact, that's the first thing that everybody thinks about. It's a great idea, right? It just turns out that it doesn't work. Okay? Well, what are we going to do about this? We could just say, forget it. You can't have negative edges. That's not allowed right now. What you can do, okay, that's not a particularly easy solution, but what you can do is you can say, let's use our kind of a combination of our weighted algorithm and our unweighted algorithm, okay? And we're going to have to, in other words, the bottom line is you have to throw out the idea of knowing anything. Like that's the problem, and that's kind of what you were alluding to, is that you really are. If you can change the ones that are already known, then it might work a little better. But the idea is that you have to now say we don't know about known ones anymore until the end, and we're going to get a drastic increase in running time. That's not good, but you got to do what you got to do sometimes, right? Here's what we do: forget about anything being known, and allow ourselves to change our mind. In other words, this is a case where that greedy algorithm isn't quite working right. Okay, you have to be able to change your mind somewhere down the line. It's like looking at that change example, right? You can't say I'm done once I've looked at them in order. You have to go back and say, is there a better way to do the change with nickels and dimes? Okay? Here's the idea. Now we're going to use an actual queue. Okay? And in lab today, you'll use queues on graphs as well to do searching. Breadth first searching through these things, and depth first searching. We're going to use a queue in this case, and you place the first vertex on a queue. At each stage, you dequeue a vertex, and then you find all the vertices adjacent such that you've got a lower cost. Okay? Well, the ones that right now are a greater cost than if you added that extra vertex, that extra edge. Update any one that needs it, and throw it back in the queue again. Okay, because you're going to have to look at it again. If you update it, you're going to have to look at it again. Okay? And you have to look through all of them. So there's no more dones. Like something could go into a queue and then pop out. You can't say it's done. You may end up throwing it back in the queue again. Right? And if it's not already in the queue, if it's already there, you don't need to put it back in there. How do you do that? You just set a little Boolean value that says to do that. Okay? By the way, in the code, I used what's called a union. I think this is the first time in my professional programming life I've ever used a union before. Bruce is going to laugh at me for saying that. But what it means is I've got two variables which are taking the same amount of space in memory. And it's so that you can print out the table right. You'll see it when you get there. Don't worry about it. It just means that you can print out the table properly. So you update it. You throw it back on the queue if it's not there already. And you repeat until the queue is empty. So what this is going to do is it's going to continually go through until you've looked at everybody that hasn't been changed, and meaning that you've gone through everybody and not changed anybody. In that case, you're done. Make sense? That's how this one works. Repeat until the queue is empty. There's a problem with this one, right? If you do have those cost cycles, again, if you could somehow go from 5 to 7 to 4 back to 5 like this would run forever because you'd constantly be updating those nodes that would be affected by the negative cost in that cycle. So you can do it by saying, I'm just going to eventually stop. I'm going to pick a point where I'm going to stop and do it. Let's see. Here's the algorithm. I'll walk this one quickly. You got your queue. You throw v1 vertex 1 on there. All right. You deal with 2 and 4. You throw them on there. The next thing you do is you dequeue vertex 2. And you deal with 5 and 4. Okay, the only one that's going to need to change in this case is 5, so 5 goes on there. I'm going through kind of quickly. Feel free to look at this on your own. Right? You deal with 5. Okay, now you get the next one off the queue, and it's going to be 4. And then you deal with 4. 4 only in this case looks at 6. Now before it looked at a lot. Now it's only going to have an edge going to 6. So you do 4. You put 6 on there. Now 5. You take 5 off, etc., etc. Let's see. When does it eventually get? I think 4 ends up going back on. Let's see, 7, and then 4 ends up back on there. Why? Because when we got to 7, we changed 4. So 4 has to go back in the queue because we still have to deal with it again. Because it changed, it may have follow-on effects, right? And in fact, it does. It actually affects 6. And so we put 6 back on the queue. Now 6 may affect other ones. So that's why it goes back on the queue. Okay? And in this case, 6 actually doesn't have any edges going to anybody, so it doesn't. But that's the idea. Deal with it. Throw it back in the queue because we're going to have to deal with it again because it may change other things. Continue until you're done. Does that make sense? Okay. All right. And finally, you are done. And by the way, now look. It did say that 1 to 2 to 5 to 7 to 4 is the best path to get to 4, right? I did not, sorry, it says it's that one. I didn't update this properly. Darn. But the point is that it did say that it did change it to be the proper negative 22 instead of 1. Okay? I'll have to update that last one. Yeah, I did it for the second one, not the last one. But otherwise, it's going to have them all right. Okay? Questions on that one? Dealing with negative edge costs? Yeah.
So you just keep doing this until the queue is empty?
Do it until the queue's empty. Yep. And again, if you have cost cycles, you have to decide. You have to say, let's see, where did I put it? Yeah, here we go. If you've got cost cycles, you have to do it. It would do it indefinitely. So you have to make a decision. If you do it, if you say everybody, the number of vertices plus 1, everybody's been seen that many times, you're at the point where you will at least have everybody pointing the right one regardless of the cost cycles. You'll get there. Okay? You have to just make a decision in that case. Otherwise, you go forever. Okay? What is the running time of this? Well, in this case, each vertex can actually be dequeued, because there's no cost cycles, can be dequeued at most the number of vertices. You could always, for every one you look at, have to re-throw it back on the queue. And if you had to do that, well, that's based on the number of edges that you've got. So that ends up meaning that you've got a running time of on the order of the number of edges times the number of vertices. Not so great. Okay, not horrible, especially if it's a sparse graph, but it's not as good as the regular Dijkstra algorithm with the log complexity. Okay. All right. Questions on Dijkstra's algorithm, the big one for graphs? No questions? Look through this if you're at all like trying to figure the algorithm out. I will ask you something about this on the final exam. Okay. So finally, I just want to give you a couple examples of Dijkstra's algorithm in the wild. We've kind of already mentioned a bunch of them. But Dijkstra's algorithm is used, or these shortest path algorithms come all the time because you build these graphs of things linked together all the time, especially in like the communications age, where you have different various nodes in some sort of a graph form, right? Example, shipping costs. So you need to get a package from here to South Korea or something, right? Well, you could go on a plane, you could go on a boat, you could go on a truck across the country, and then on a boat or plane or whatever. There's going to be routes that are based on costs, right? Maybe it costs too much money to fly it there because of the fuel costs in the air, right? Or the weight of it has to, it's so heavy that it's going to cost more to fly it there than to drive it to point A to point B. What if you need to get it there the fastest, right? That's going to end up the shortest path time, right? Your cost is going to be the time. Computer networks, anything dealing with networking, right? If you take a networks class here, I can guarantee you'll talk something about shortest paths in some form or another. Telephone networking, which are really computers. Best path for a call to travel, we talked about that. Should it go to the satellite? Should it go across the ground? Should it go between cities? Right? Any other type of path. Shortest paths for traveling in maps, like subways, right? You need to get from here to the airport or something. Now the government station's closed. Oh man, how do you do it, right? Right? So you've got to figure out their shortest path. And there's various bus routes and subway routes and Uber routes and all that kind of stuff, right? Maze. What if you have a maze which has different solutions that are shorter or longer? You're going to be able to use some sort of shortest path algorithm. Dijkstra's itself doesn't necessarily work that great on mazes, simply because it doesn't necessarily go in the right direction, but it will find a shortest path. It's a little different, but shortest path algorithms are used for finding the shortest path through mazes that have multiple solutions. Okay. All right, and then this is still somewhat of a topic of discussion. People are still using this. This is a paper from the year 2000, so not too long ago. A while ago at this point, I guess, 14 years, but not too long ago. It's talking about using Dijkstra's algorithm for like public railroad transport. In fact, the computers that have to, it's talking about the computers that have to actually take everybody's input and then decide what the best route is for them. Okay, so people are still talking about this stuff. It's not just because it was done in the 50s doesn't mean it's everything's solved about it. Okay. And I think, yep, the reference is there. If you want to look at the visualizations, if my visualizations up here didn't work for you, the visualizations page that we've gone to a number of times has a very good one. It does it for weighted graphs, non-weighted, directed graphs, non-directed, all that stuff. It's pretty good if you want to look at that. All right, questions? Dijkstra's algorithm, graphs, homework 5. Anything else? OK, I'll see you guys Wednesday or in lab.